Hello guys, this is Dev again. Today we are going to learn about force. Okay. So force is governed by Newton's three laws. Okay. I'm going to start with the first law. The first law says a body at rest will remain at rest and a body in motion will remain in motion until and unless an external force is applied on it. Okay. So what does this mean? Let us take an example. This is a block of mass m and it is moving. The surface has no friction force. Okay, friction is zero. All right. So to stop this body, I need an decelerating force. Okay, otherwise this body will not stop. It will continue in the same trajectory it was following before. And if a body is at rest, let us consider in the first part the body had velocity v. Here velocity v is 0. So we need either we need an accelerating force, not a decelerating one. Okay, we need an accelerating force to get this body moving. So if the force is 0, the body will continue to do what it was doing before. All right, but if the force is not 0, the body, the state of the body will change. State of the body will change. This is very important because the body is defined by its state. Okay, so force should be non-zero for changing the state of body. All right. Now we come to Newton's second law. Everyone knows Newton's second law is described as F equal to ma, but F equal to ma is not the second law, okay, but a consequence of the second law. Second law states that force is the result of change in momentum. This is the second law, okay. So for change in momentum we have F equal to dp, right, but force is the rate of change of momentum actually. This is the second law. Okay, so P equal to mass into velocity. As mass here is constant, we are not taking the relativistic situation. Velocity v is very less than the speed of light. Okay, so mass here is constant, hence it can come out of the differential as dp by dt will be d by dt of mb. So m will come out and this will be m dv by dt. This will be equal to f, and dv by dt is the rate of change of velocity, which is known as acceleration. So f equal to m is a consequence of second law. Okay, so let us take an example. Suppose this is a surface, okay, and this is a horizontal surface and this is a normal to the surface. Suppose a particle has a velocity v here. Okay, particle has a mass m. It strikes the surface at an angle theta, okay, and rebounds with the same velocity at an angle theta. Okay, so has the particle experienced any force? Yes, it has. Okay, why? Because the momentum has changed. Momentum has changed. Okay, even if the magnitude is same, because momentum here is mv, here also it is mv, so magnitude of p is constant. But how come it is changed? Because the direction has changed. Okay, even if direction changes, the force will be applied. Okay, so what will be the force? We will see the direction. This is a horizontal surface, and okay, so we split the momentum. Okay, this is p, and force, since force is change in momentum by change in time, so change in momentum would be final momentum minus initial momentum, and this will be vector. Don't take it as scalar. Okay, this is vector because magnitude is not changing. I specified it in the question. So mod of p will be constant, but force will be applied because the direction has changed. All right, so what will be pf? We resolve the pf into two components. You see the final direction of particles like this, so we can resolve it. Consider this as x-axis, okay, this has y-axis. So this will be mv cos theta and this will be minus mv sin theta j. Okay, I have considered the left side as x-axis. Okay, so this will be positive. Okay, don't confuse it. All right, this will be minus mv sin theta j. Alright, this is the position of the final momentum. So final momentum Pf would be equal to mv cos theta I minus mv sine theta j. Okay, and what will be the initial momentum? Initial momentum is, the direction is like this, so we can resolve it into two components again. Since I have assumed this direction as positive x-axis, so this will be negative, so this will be minus mv cos theta. Why? Because since this is theta, this will be theta. Okay, minus mv cos theta I, and this would be equal to minus mv sine theta j. Okay, so what will be pi? Pi would be equal to minus mv cos theta I, yeah, minus mv sine theta j. Alright, so let us solve. Pf minus pi would be equal to twice mv cos theta I. Alright, divided by time interval. Whatever time has been taken, it does not matter, it will be specified. So force here is this. You see, it is not zero, even if the magnitude is same. So what we conclude is the direction of momentum also matters. Okay, do not take just the magnitude. Alright. Now I want to take up one more important concept, that is of reference frame. Okay, reference frames, and the concept is of inertial and non-inertial frames. So what is this inertial and non-inertial? I'll tell you. First of all, let us consider the frame S. Okay, there is a particle P inside the frame S. Particle P has coordinates x, y and z. Okay, the radius vector drawn from the origin of S to particle P is r, say. So r would be equal to xi plus yj plus zk. Okay, and what will be dr by dt? This would be equal to dx by dt I plus dy by dt j plus dz by dt k. And acceleration would be d square by dt square. You can write it down. Okay, double differential, all of you know. Okay, so what is inertial frame? Inertial frame is a frame which moves, either is the frame which is either static or which moves with a constant velocity. Alright, so say S dash is a inertial frame. So this was S. Okay, say S dash is an inertial frame, for example like this. If S dash is an inertial frame, either S dash is constant, is moving with a constant velocity, or either S dash is at rest. Suppose S dash is moving with a constant velocity v. The particle was here. Alright, from S the particle P had coordinates x, y and z, but this was the coordinate with respect to S. But what will be the coordinates with respect to S dash? Because it is going parallel to x. Okay, say this is x dash, this is x, this is going parallel to the x axis of S frame. This means the x coordinate will get reduced by vt. So the coordinates in the frame S dash would be equal to x minus vt, y and z. Alright, these would be the coordinates of the particle P with respect to S dash. Okay, so if we draw a radius vector from the point O dash of the origin of S dash, this would be equal to r dash, and this would be x minus vt comma y comma z. Alright, so the r dash radius vector would be equal to x minus vt I plus yj plus zk. Okay, so r dash equal to x minus vt I plus yj plus zk. So what would be dr by dt? Dr dash actually. I have assumed v as constant. Okay, so this would be dx by dt minus v, and this would be I plus dy by dt j plus dz by dt k. And what would be the double differential of this? This would be equal to d square x by dt square plus we will get cancelled, because you know the differential of a constant is 0. Alright, d square y by dt square j plus d square z by dt square k. And we know this was the original acceleration with respect to the frame S, and this is the acceleration with respect to the frame S dash. So you see, the acceleration is same. This means if a frame is inertial, then transformation of coordinates is invariant in case of acceleration. So We have transformed the acceleration and it is invariant. Alright. So this is the meaning of inertial frame. Alright. Now say I take non-inertial frame. Non-inertial frame, say S dash moves with the acceleration A. And now I have assumed this acceleration as constant. Okay. Because if acceleration is varying, there will be many difficulties, and the standard I am taking, the standard notation I am taking. Okay. So what were the coordinates of P with respect to X? There were X, Y and Z. Okay. And now I want to calculate the coordinates of P with respect to S dash. Alright. So you see, this is again S dash is moving parallel to the X axis of S. And now it is moving with a constant A. It has started with an acceleration A. This means the X coordinate now will get reduced by half AT square. Because the initial velocity of the frame S dash would be equal to 0. As it has started from acceleration A. Okay. So the point P will have X coordinate as X minus half AT square. Y and Z will be same as it is not moving parallel or parallel to them. So these are the coordinates with respect to S dash. Alright. So now what would be R dash? Since this is R dash would be equal to X minus half AT square I plus YJ plus ZK. Okay. So dr dash by dt would be equal to dx by dt. Since acceleration is constant, this would be minus AT I plus dy by dt j plus dz by dt k. And what will be the double differential of this? This would be the acceleration with respect to S dash. Okay. And mind it, particle P does not have a constant velocity. It can move because it has variable coordinates. X, Y and Z obviously are varying. They are not constant. Okay. And this would be equal to d square x by dt square I plus d square y by dt square j plus d square z by dt square k minus a. This was the acceleration of the particle with respect to the frame S, and this is minus a, and now we can conclude that the acceleration of the particle with respect to S dash is the acceleration of particle with respect to S minus of a. So you see, the transformation of coordinates is not invariant. Is not invariant. Okay. Okay. The transformation of coordinates here is not invariant. This is the meaning of non-inertial frame, when the transformation of coordinates becomes not invariant. Okay. In inertial frame, I am once again repeating it. Transformation of coordinates is invariant. Okay. As we saw with acceleration. And in non-inertial, it is not invariant. Okay. Now relating to second law, I want to take an example. Everyone must must have seen this system. It's known as pulley. Okay, this is the rope and these are the two masses M2 and M1. Alright, here a general assumption I make. First of all, M2 is greater than M1. So any one of you can tell what will happen. M2 will go down and M1 will come up. Okay, so we can, first of all, for writing equations of motion, you first draw a separate diagram of the mass. For example, this is M2. Alright, in a free body diagram, what we will depict here is the forces on this mass, not the forces applied by this mass. Okay, so the forces on this mass are due to gravity, which is M2g, and due to tension of the string. Okay, and since it is going downwards, then that means gravity is more than tension. So M2g minus t. Okay, this would be equal to M2 into A. Alright, and now this is mass M1. So the forces on this are tension T and the gravity, and since it is going up, so the equation of motion would be T minus M1g equal to M1A. Right, now I want to ask you a basic thing. Why are the tensions same? First of all, you let me know why I have written TT as same. It can be different because masses are different. And why is the acceleration same? Why is the tension same and why is the acceleration same? Okay. Because in a pulley system, two assumptions are made. Okay. What are the assumptions? First, string is massless or has negligible weight, negligible mass actually, and string is not stretchable. Okay, these are the two assumptions made in a pulley. All right. These two assumptions, by using these two assumptions, we arrive at the same tension and same acceleration. Okay, I'll show you how. Suppose there is a block of mass M kept and this is a rope. Okay, at this point P, a force is applied and the force is taking the whole system with an acceleration A. This means that the rope is also going with an acceleration A. All right. Since the rope is very, very thin, okay, and very extended, we denote a quantity known as lambda, which is mass per unit length. Since, rope is long, we will have to, for example, if we have to find out a mass of a certain portion of rope, that will be denoted by lambda. Okay, and this will be taken from the mass M. Okay, so suppose this is the rope and I have to take, for example, the mass of this portion. Okay, and this is the block of mass M. I am assuming origin over here and I am taking the distance from this. This has a very small width known as dx. For a very small quantity, delta x or dx, you assume anything, it is the same thing. Okay, because it will always reach infinitesimal value and it will be dx. And this mass dx is at a distance x from the mass. Okay, so what is the mass of this portion? This portion has mass as lambda dx, which is equal to dm. Okay, dm is the elemental mass of this portion. So now I want to draw the free force diagram of this small portion. So we take this small portion, and as I told you earlier, the force body diagram is we will only depict the forces applied on the mass, not by the mass. Okay, so forces on the mass are tensions from the two sides. Say these are different. For example, this is dt dash and this is dt. All right. Since the rope is also accelerating with the mass, this means the rope is in acceleration and this force is more than this. Okay, so this means dt dash minus dt equal to dm into a. All right, this is it. Here the tensions are not same. All right, because of mass. Had the mass dm been negligible, now we assume it as negligible. This means dm is reaching 0, so we can assume this as 0. So dt dash would be equal to dt. Hence, the tensions are now similar. This means at each and every point on the rope, same amount of force will be applied or same amount of tension will be there. Tension is distributed now. That's why in a pulley, you see there are two different mass M2 and M1. Tension along the rope is same because of this concept. All right, negligible mass. Now another of the same acceleration. All right, there is the second question was of same acceleration. First of all, let us draw this figure. Let us assume a thing that in the first case the two masses are kept at same level. All right, since M2 is greater than M1, obviously this will go down and this will come up. So after a certain point of time, the figure will be like this. Yep. All right, so now the string is non-stretchable. All right, I have assumed this string is non-stretchable, so the length of string will be constant at any point of time. L equal to constant. Okay, so suppose this length was L1, this was L2. Okay, and this length of string going over the pulley was L3. This will remain essentially the same because the points, the attachment of point of strings are same. So even if this goes up, the length of the string attached to the pulley or going over the pulley would be same. So this will also be again L3. And now I suppose that mass M2 has displaced a displacement as x2 and mass M1 has displaced x1. Okay, so this is L1, and since this was L2, it has gone up, so this would be equal to L2 minus x1. Okay, so now what is the length of string in this position? It is L1 plus L2 plus L3 equal to L. What is the length of string here? That would be L1 plus x2 plus L3 plus L2 minus x1, right? This would be equal to L. So these are same. I told you string is not stretchable. Since these are same, equate the two, and L3 will cancel, L1 will cancel, L2 will cancel, and we have x2 minus x1. x2 minus x1 would be equal to 0. x2 is equal to x1. Since the displacement are same, hence the double differential of the displacement, which is d square x1 by dt square equal to d square x2 by dt square would be same. So a1 equal to a2. This is the correct method of derivation of same acceleration, and now you are in a position to solve the question. Okay, so the question was the equations were m2g minus t equal to m2a, and this was t minus m1g equal to m1a. Now we know why the acceleration is same and the tension is same, so this gets cancelled. Okay, so the final answer is m2 minus m1 by m1 plus m2 into g. This is the final answer of acceleration. Alright, just remember this is the final answer of the acceleration of the pulley system. Okay, alright, so now we study another system known as the inclined plane. Okay, so in an inclined plane, suppose this is an inclined plane ABC. This is 90 degrees and this angle is theta. Alright, and a particle is kept on the surface of the inclined plane. The surface of inclined plane is AC. Alright, the particle will move along this surface only, and this is the ground, horizontal. Okay, so I now want to know, for example, say if the particle is of mass m, what are the forces on the particle? Just tell me. Okay, first you draw this surface and this is the particle. So in a free body diagram, we always draw the forces on the particle. Right, so there will be one force on the particle due to the surface, which will be perpendicular to the surface AC. Alright, and there will be one force of gravity mg. Okay, and this is the angle of the inclined plane theta. Alright, so no question over there, and this is 90 because the force would be perpendicular to the surface. Alright, since surface is exerting on the particle. Okay, so now I draw a parallel line. Okay, since this is theta, this must be theta, and since this whole is 90, this must be 90 minus theta. Alright, okay, so you got it. And just I extend this, and this is parallel to this. Okay, this axis is parallel to this. Alright, so since this angle is contained between these two lines, this angle has to be equal vertically opposite angles. So this is 90 minus theta, and this an axis parallel to AC will be perpendicular to n, and hence this angle will be theta. Alright, and this angle would be 90 minus theta, as mg is perpendicular to the floor. So since this axis is perpendicular to mg, this will be 90 minus theta angle. Alright, so I want to take the component of mg along this line. This would be mg sine theta. Alright, and this will be theta, and the component of weight along this line would be mg cos theta. Now you see why I am taking the component. First understand this. This is because the particle is moving along this surface. Particle is not moving along here. And this means if normal is there, then there must be some other force to balance this, because particle is not moving here. So if there is n, this force would be the component of the weight, which is mg cos theta, and the force driving the particle along the surface AC would be equal to mg sin theta. All right, so these are the equations, and n would be equal to mg cos theta. Since the surface is not going anywhere, particle is not moving along n, and mg sin theta would be equal to the mass into acceleration, and this gets cancelled out, so a would be equal to g sin theta. Right, this is the acceleration along the inclined plane. Okay, now I take another case, pendulum. So what is a pendulum? It is nothing but an object suspended from a string, and consider a string of length L and mass m of the object. So here, if I for example I want to first calculate the free body diagram of this, the free body diagram of this situation only, the particle has not been displayed. Okay, so this would be like this, the tension of the string, and this would be the weight of the particle, and this is the mass of the particle, hence mg would be equal to t, as particle is not moving. All right, this would be the free body diagram of this situation. If say the particle has been displaced by an angle, say this angle is theta, all right, length of string will remain same. Okay, it is not changing. Now I want to know the equations of force on the particle. There were two forces first, one was tension and one was the weight. Since particle has been displaced, the tension will be along the string only, but the weight will be downright. Okay, it will be parallel to this. So the equations have changed now. All right, and if since this is the horizontal, so the particle has been displaced, and this is the weight, this is tension, this is the angle theta, so this would be theta and this would be 90 minus theta, right? So the component of tension would be t cos theta, and this component would be t sin theta, right? So t cos theta would balance out mg, because the weight, the mass would travel along this side, it is not going down, so this means tension would balance the weight. Component of tension can balance the weight. Okay, so t cos theta would be equal to mg, and t sin theta would be equal to ma, right? So what will be t? T will be equal to mg divided by cos theta. This would be equal to t. Right, so these were the equations. Okay, t cos theta was mg and t sin theta was ma, because particle is going here, only force driving the particle or accelerating it is t sin theta. Particle is not going vertically down. Okay, consider it horizontal because angle is very small. Okay, I have extrapolated this, but in reality the angle is very, very small, like this. Okay, this is theta. Theta is essentially very small, and hence the particle can be understood to go horizontally. In this figure it looks particle is as if it has a vertical motion, but it in general does not, because the angle is very small. So essentially the vertical component of t balances out the weight. Okay, sorry, this is cos theta, t cos theta, and you see this is almost a horizontal line. Okay, this is what I want to emphasize. Okay, so here we can see tan theta, we just divide these two equations, will be a over g, and a will be equal to g tan theta, right? A would be equal to g tan theta. So now you see this acceleration is what is called a restoring force. Okay, so what is tan theta? If a minor displacement has occurred, okay, and angle is very small, so what will be tan theta? For example, this, if this is consider if this is x. Okay, if this is x, then tan theta would be equal to, this is 90, right? So x over L. So tan theta would be equal to x over L. This will be clear from this diagram. This is x, this is theta, this is 90, and this is L. This is also L. Tan theta would be equal to perpendicular divided by base. So x over L. Alright, so A would be equal to Gx over L. Since displacement is in the negative direction, so x would be minus, so A equal to minus Gx by L. And since A is d square x by dt square, everyone knows, so this would be equal to minus Gx over L, and this can come here, so this will be d square x by dt square plus Gx by L equal to 0. Okay, you see I have written A as minus Gx by L. This is because essentially this is a restoring force. For example, if I say this is a spring and this is a mass, okay, I have pulled the mass over here, but the force is in this direction. Okay, the spring, this weight. Okay, for example, consider this is a spring and this is a mass. A force is pulling the mass over here, but the string exerts a force in the negative direction, although the displacement is in the positive direction of the mass. Similarly, in this pendulum, you see the angle is very small, right? The displacement has been in positive direction, but the tension is the restoring force. So you see T sine theta equal to ma. This is the restoring force over here. Okay, so T sine theta is actually negative. Okay, just like this spring. Spring is exerting force in the negative direction, although the displacement is positive. Alright, but had the pendulum been displaced like this, then also the restoring force would be along the different direction of the displacement, or you can say the opposite direction of displacement. Alright, this kind of force, which opposes displacement anywhere is called restoring force. Okay, restoring force. So this will be taken as negative, hence A would be equal to minus Gx by L. So I had arrived at a conclusion d square x by dt square plus Gx by L equal to 0. This is known as simple harmonic equation. This is known as simple harmonic equation. Alright. D square x by dt square plus Gx by L equal to 0. Simple harmonic equation definitely means either the solution is sine function or cos function. So a solution of x as a function of t will be either sine function or cos function. Okay, this is definitely the meaning of this solution. Alright, so now to solve this equation, let us assume something. Let us assume solution is a sine omega t. Alright, plus phi. Alright, plus phi can be 0 also, or phi can have some value. Alright, it does not matter. For simplicity, let's say x is a sine omega t. Alright, so now d square x by dt square, what will be this? First differential will give a omega cos omega t, right? And second differential, again the differential of cos would be minus. So this would be a omega square sine omega t. Okay, so let us write this down. Minus a omega square sine omega t plus g over L, and x was a sine omega t. This equal to 0. So you see sine omega t gets cancelled out, a gets cancelled out, and we are left with omega square equal to g over L. You see this omega is the frequency. Alright, you see the sine function when we have taken, then in the bracket there must be the value of angle, and this is time, and since angle has no dimensions, the omega would be the reversal of time. Alright, the inverse of time we can say. Okay, so inverse of time is the frequency, everyone knows. So omega equal to root g over L. Okay, so what would be t? In general terms, omega is 2 pi over t. In one cycle, in sine cycle for example, the cycle repeats itself. Okay, so for example this in 2 pi, this is 2 pi. Alright, this is pi. It is this from 0 to pi it is not repeat, from 0 to 2 pi it is repeat, because at 0 sine was 0. Okay, and although because although at pi it is also 0, 2 pi it is also 0, but from 2 pi it will start again. Okay, from the positive as it did from 0. So this should be same. Hence one cycle is complete from 0 to 2 pi. So time taken from 0 to 2 pi would be 2 pi by omega, and we can write this as omega equal to 2 pi by t. So just substituting this, we have 2 pi by t equal to root of g over L, and t we have here is 2 pi root L by g. This is the time period of the pendulum. Alright, this is the time period of a simple pendulum, 2 pi root L over g. Now the next I want to come is on collision. You see, the force is the change in momentum divided by time, right? And now in a collision, for example, we have m1 and its velocity v1, m2 and its velocity v2. All velocities are constant over here. Just remember, first of all right, now they collide. This is the situation before collision, and this is the situation after collision. You see, the velocities have changed, v1 dash and v2 dash, but still v1 dash is constant, v2 dash is constant. I have assumed that. Alright, now we generally do what? We generally conserve the momentum, right? Why is it conserved? First of all, I want to know. This is because, first of all, you see, when is the momentum will be conserved? You see, dp equal to f times dt, right? Alright, so when a momentum will be conserved, dt cannot be 0, time is never 0, so force has to be 0, alright. Then dp will be equal to 0 and p will be equal to constant. Alright, integration of when a differential is constant, then its integration, when a differential is 0, then its integral is constant, because a constant has a 0 differential. Okay, so only p will be constant when f is 0. Okay, and that too, this is external force, because we are considering a system over here. So I want to see first how, because when m1 is traveling with v1, there is no external force on m1. Okay, there is no external force here. It will keep on traveling with v1 as I stated in the first law. And now m2 is traveling with v2. Obviously there is no external force here, because they both are traveling with a constant velocity. Now an event arises when they collide. When they collide, you see, this is the situation, right? This is m1 and this is m2. Now what happens is, there is an interaction between them. Okay, due to this interaction, perhaps m1 will lose some velocity or m2 will gain, or the vice versa will happen. Okay, this interaction between these two will not be counted, because we are considering f equal to 0 as external forces. Alright, because the f here, which is 0, is the external forces, and these are counted in the internal forces, and internal forces always gets cancelled out. Alright, this is because of Newton's third law of motion, where action equal to reaction. Every action has an equal and opposite reaction. This is not true in most cases. This is not true in most cases, just like magnetic field, relativity, but nonetheless we are considering a standard problem over here, so this will get cancelled out. Okay, this is what I want to really emphasize upon. So you see, this is m1 and this is m2. This is m1 again, this is m2, but to change velocities, v1 dash and this is v2 dash, this is v2 and this is v1. So since external forces is 0, so dp would be equal to 0, p would be equal to constant. Hence the system's momentum before collision was m1 v1 plus m2 v2. Okay, why? Because both are in the same direction. You see, I have taken this direction as positive I. Both are in the same direction, so total momentum of the system will consist of the individual momentum of the masses added together. And after collision, what will be the momentum? This will be like this: m1 v1 dash plus m2 v2 dash. Okay, this is the first equation. This has been derived from external forces which are 0. Okay, and in turn this has led to a constant momentum. Now the next thing is that the collision is elastic. Collision is elastic. Elastic means that there is no energy loss in, sometimes we see that energy is lost as a form of heat. Okay, but here there is no such thing, energy is not lost, hence the net energy is constant. before and after the collision. So what was the net energy? Since they are only moving around along a flat surface, the only energy they can have is kinetic. The only energy they can have is of kinetic energy. There is no rolling over here, okay? Don't consider them as balls and you start rolling them over and consider rotational energy. No, there is only kinetic energy over here. So this will be half m1 v1 square plus half m2 v2 square. This is the kinetic energy before collision, equal to half m1 v1 dash square plus half m2 v2 dash square. This is the kinetic energy after collision. Okay. Okay, so before we proceed further, I would like to teach you about work done. Alright, work done. What is work done? And I would like to in turn teach you about kinetic energy. First of all, you start with work done. What is the work done? Work done means, for example, if this is a block of mass m, okay, and this is a force pushing the block, and this is a wall. The wall is held up against the block is held up against the wall. Okay, the block is not moving. Force is continuously pushing the block for example, for say 4 hours. What is the work done? Work done here is 0. Okay. Say for example, if force pushes a block and block moves now. The block moves from here to here, from A to B. Okay. It has traveled a distance x. What is the work done now? Work done is not 0. Okay. It is not 0. Alright. And now I am assuming this force is conservative. Okay. I will explain you everything. Just, be with me right now. When the block has been displaced, the work is not equal to 0. Okay. But for example, if I say this is a particle at A and a force is being applied at a particle, and the force is, taking the particle to a path and taking back the particle to the same point A. What is the work done in this situation? This will be 0. Because force is conservative over here. Okay. What does this mean? Conservative force as such is path dependent. Conservative force is dependent on path. As such, the basic definition of work done is the dot product of force and displacement. Okay, here ds is the displacement. Just remember it. Why is it the displacement and not the distance? This is because you see work is a scalar quantity, and since LHS is a scalar, RHS has to be scalar, and since work is the multiplication of force and the displacement, there has to be displacement. It cannot be distance because force is a vector, and the dot product of two vectors is a scalar. Okay, dot product of two vectors is a scalar, so work done has to be a scalar. Okay, so this quantity must be displacement. It cannot be distance, as distance is a scalar, so dot product will not be applicable. Okay, so since this is a displacement, in earlier question I asked you that when a particle starts from A and is brought back to A by a force, then work done is 0 because displacement is 0. Okay, it has gone away from A and come back to A. So during this whole time, the displacement ds was 0. Okay, displacement is 0, so work done is 0. Alright, now I have assumed this conservative force because there is no other force acting on A. Had there been any other force, for example friction, the work done by friction wouldn't, cannot be taken into account because friction converts the work into heat. Work done by friction is lost into heat, is lost as heat. So the account of taking account of this work is very difficult. That's why I have omitted this friction. Friction is a non-conservative force. Now what does this mean? You see, force is conservative when it is only path dependent. Okay, F equal to F of R. What does this mean? For example, if a particle is traveling in a circle, okay, and this is a thread. This thread is, making the particle go in a circle. So what is the force being applied on the particle? Obviously, this is the tension T. This is the only force. And what do we know from a circle? If a particle goes with a constant velocity v, then this means tension is causing acceleration of particle, and since velocity is constant, there will be only one acceleration, which will be centripetal acceleration. So centripetal acceleration would be equal to v square by r, as discussed earlier, okay, and tangential would be 0, because tangential acceleration is dv over dt, as v is constant, so it will be 0. So what is the force? Tension is mv square by r, okay. So you see here, tension is a conservative force because T is solely and wholly dependent on R, as M and V are constant. So T can be written as K over R, okay. So tension is a conservative force over here. So forces are conservative, which are only dependent on the path, okay, only dependent on path. It depends on nothing else, okay. Elemental work done was F dot ds. Alright, this was the element work. Now we just do a little manipulation in this expression. You see F is ma, so this will be A dot ds. What was A? A was dv over dt, right? So we substitute the value of A in this equation, we get dv by dt dot ds, okay. We just take this ds over dt, so dw was m dv dot v, okay. This is the expression for work done, okay. Now I want to point out a few things. In normal situation, when a particle is going in a straight line, v and dv are parallel, right? Because some change will be either anti-parallel or make the dv parallel. For example, if a velocity increases, then the dv direction would be parallel, okay. If it decreases, then it will be anti-parallel, okay. So here we assume that it is parallel, okay. So mv dot dv, sorry, so this would be mv dv, since cos theta, right, when parallel theta becomes 0, so cos 0 is 1, so mv dv equal to dw. So we can integrate this, okay. So now we integrate this from v1 to v2 and this from 0 to w, assuming work done is 0 initially. So work done would be equal to half m v2 square minus half m v1 square. So you see in this expression is a change in kinetic energy, because kinetic energy is half mv square. Kinetic energy is only dependent on motion, it is dependent on nothing else, okay. So work done is the change in kinetic energy. This is what I want to emphasize in that momentum equation. And work done is obviously F dot ds. We have arrived this work done as from F dot ds, okay. So now, for example, if a particle was not thrown, just dropped, okay, from a height edge. Particle was just dropped from the height edge and it reaches a point, for example, P, which is at a height, for example, h over 2. Now I want to find the work done. From O to P, what is the work done by the particle? What is the work done by, actually not the particle, it will be gravity. Now you see the only force acting on particle is mg, nothing else, because it has been dropped. Initial velocity is 0 because it has been dropped, alright. So the work done by the gravity will be F dot ds, as I told you earlier, okay. F is downward, so it will be minus j. Displacement is also downward, so it will also be minus j. And what will be the displacement? OP. And what is it? Since this total height is h, this would be h over 2. So this would be equal to mg minus j, yeah, dot h over 2 minus j, right? This gets 1, minus 1, j dot j is 1, so mg h by 2 is the work done, okay. Mg h by 2 is the work done. This is the potential energy of the particle at point P. So now what I want to emphasize is, we can view this work done in another form also. You see, since the initial velocity is 0, so the displacement in the second equation of motion was half gt square, right? Because s will be minus, g will be minus, minus will cancel out, so it will be plus. So h over 2 equal to half gt square. So what is t over here? T is root h over g, right? What is the change in kinetic energy from O to P? What will be the velocity? Velocity would be equal to g into t. And what is t? T is root h by g, so it will be root hg. So what will be the kinetic energy? Half m v square is hg. So mg h by 2. Since here u was 0, initial kinetic energy is 0. So you see both expressions are same. So what do we conclude with this? We conclude that f dot ds equal to delta ke, which I derived earlier. This is the negative change in potential energy. Why? Because you see, when particle was at this point, the potential energy was mgh, and when it has come to this point p, the potential energy is mgh over 2. So you see, potential energy, when it decreases, then it leads to increase in kinetic energy. Okay. Had the reverse happened, for example, if a particle was thrown up, when it was thrown up, you see potential energy was increasing from h by 2 to h, but its velocity would have been decreased, because at final point its velocity would have been 0. So negative of delta u equal to positive of delta ke. Okay. So u2 minus u1 minus equal to k2 minus k1. So u1 plus k1 equal to u2 plus k2. Alright. So in the momentum equation, we took only kinetic energy. This was because potential energy was absent. The two particles were on the ground at all point of time. Okay. So this was half m1 v1 square half m2 v2 square equal to half m1 v1 dash square plus half m2 v2 dash square. So this was v2 dash, this is m2, this is v1 dash, this is m1, this is v2, this is m2, this is v1, this is m1. Okay, this this is a situation before collision, and this is a situation after collision. And we also had another equation, m1 v1 plus m2 v2 equal to m1 v1 dash plus m2 v2 dash. Okay, now please, every one of you can solve it by yourself. Okay, just tell me what are v1 dash and v2 dash. Just write comment below what are v1 dash and v2 dash, and what is the final kinetic energy, final ke. Okay, so we now take the case of a circle. For example, if a particle has been made to travel around a circle by a string T, string has tension T. Okay, this is a particle and this is going with a constant velocity along a circle. What is the work done? For example, say from point A to point B, what is the work done? This work done would be 0. Why this is so? First of all, why this work done is 0? Because the displacement of the particle t dot ds will be 0, because t will be perpendicular to ds, as t is along the radius. Okay, t is along the radius, and displacement will be along the tangent. Okay, so along the direction of velocity. So t is perpendicular to ds and t dot ds is 0, so work done is 0. Now there is another explanation for this. As velocity is constant, okay, and particle is going around a circle is not at any height, so particle's potential energy is 0. Now I know that work done is a change in kinetic energy, right? What is the kinetic energy at A? Kinetic energy at A is half mv square. What is the kinetic energy at B? It is also half mv square. So this gets cancelled out, work done is 0, as particle is moving with a constant velocity. The magnitude of velocity is constant. Okay, and you know, as kinetic energy does not depend on direction, it does not matter where the velocity vector is going, only matters is its magnitude, and this is constant, so the work done is 0. Alright, now this is another situation where there are two bodies, m1 is moving with v1, m2 is moving with v2, and then they collide. After collision, m1 and m2 stick together and the whole system moves with another velocity v. This kind of collision is known as inelastic collision. Okay, inelastic collision. In inelastic collision, kinetic energy is always lost. Alright, so we will write the equation of momentum, because momentum will remain conserved, as even when m1 and m2 are joined, the internal forces will cancel out. So m1 v1 plus m2 v2 equal to m1 plus m2 into v. Alright, momentum will be constant. Alright, just remember it. As there is no external force on the system, momentum has to be constant. So what is the final velocity v? m1 v1 plus m2 v2 divided by m1 plus m2. Alright, this is the final velocity v. Here we cannot equate the kinetic energy, as kinetic energy will be lost. So Ke will be lost here. So Ke will not be conserved. So we can only calculate the loss in kinetic energy. That's it. Okay. So the loss in kinetic energy will be final Ke minus initial Ke. What will be this? Final Ke would be equal to half m1 plus m2 into v square minus half m1 v1 square minus half m2 v2 square. What was v? v was m1 v1 plus m2 v2 the whole square by, this gets cancelled out, so this will be 2 into m1 plus m2 minus half m1 v1 square minus half m2 v2 square. So just expanding this expression we have and this is twice of m1 plus m2 minus half m1 v1 square minus half m2 v2 square, right? So solving it now, we take v1 here, so this would be equal to m1 square will get cancelled out, half will be outside, m1 square will get cancelled out, right? So this would be equal to minus half m1 m2 v1 square by m1 plus m2, and what will be this? m2 square gets cancelled out again, this will be minus half m1 m2 v2 square by m1 plus m2. Okay, so this would be in totality minus half m1 m2 divided by m1 plus m2 v1 square plus v2 square. This is the loss in Ke. Why this is negative? Because kinetic energy has been lost. Final kinetic energy is less than initial. That is why a negative sign has appeared. Alright, so this is it, and this expression m1 m2 upon m1 plus m2, this is called mu, and this is reduced mass. Okay, so mu by 2 v1 square plus v2 square. This is the final change in kinetic energy, which is negative. Alright, so guys, this was my analysis. Okay, please like, comment, rate, whatever, and please remind me if I have missed something. Okay, I'll make more videos, and bye for now. Okay, thank you.